Okay, let me continue now with round robin. Now, round robin, here's an example for round robin. So remember, round robin assumes preemption. And so in this case, we assume the time quantum of 20 time units. And so then these are the different processes with burst times. And you may assume they are released at the same time, but in other cases, they may join later. So in this example, they all are available. So, but then in the order of P1, P2, P3, P4. So no matter what their burst time is, you just run them in order up till the quantum. So like here, 20 out of 53 is executed, and by the time you've done 20, you switch context to P2. Even though P2 is shorter, it will still wait its turn, but then it does finish before the time quantum. So what do? Well, you don't have to wait till the time quantum expires. You actually reset the time quantum at the time of completion, and then you go to P3 to run P3. P3 has 68 CPU bursts total. You run 20, and then by the time you finish 20 at time 57, you switch context to P4. P4 has 24 time bursts. You use up 20 and then switch context back to P1. P1 does another 20, switches to P3. P3 does another 20, switches to P4. P4 now only has 4 remaining, so it finishes its 4. And so it doesn't have to wait until its quantum expires, right? It's only using 4 out of 20. So the time quantum part, or timer gets reset from beginning. So that means by the time you come back to P1, it doesn't just get the leftover quantum. It actually gets its 20, okay? So then it runs for 20 again, then P3. When P3's time quantum is up, well, everybody else is finished. So the scheduler puts it back, so it continues finishing up its remaining CPU bursts. So that's an example of round robin. Now, so round robin is one that may seem more fair because it has no starvation, but it's not always the best one, just depending on your criterion. Now, best, what does it mean to be best? Well, really it has to be put into context. So that's why there are many different schemes, and they are called what's called priority-based scheme. Now, priority refers both to the mechanism of some kind of priority queue, priority scheme, as well as priority in terms of how an application prioritizes the different tasks it has to execute. So now, but in general, this is, you can think of it as a framework for defining different scheduling techniques. So priority-based means for each process, you define some kind of priority value, which then you can put into a priority queue. Remember priority queue from your prerequisite quiz? Say yes. Use a heap, right? Remember heap data structure? It's an array, but then you structure it kind of like a binary tree. So it takes log time to extract and fix it up, right? And so you can do heap sort if you want. I mean, that heap is not the same as the dynamic allocation heap. That's the data structure heap. That's one way of doing priority queue. There are other ways doing priority queue, and you use that because it's very quick to extract, quick to maintain that data structure. You don't have to do full sorting. And so that is why these priority-based scheduling techniques are used. And in fact, the priority itself could be static or dynamic. In other words, it could be assigned at the time of process creation and remain fixed value, or as a process runs, its priority could go up or down over time. Well, that would be dynamic priority. So if we go back to shorter job first, yes, in fact, it is, or it can be viewed as a priority scheme. Why? Because the priority is given to shortest remaining burst, right? Whoever has the shortest remaining burst has the highest priority. And so, in other words, it's defined to be inversely proportional to the length of the next CPU burst. First come, first serve, well, it's kind of a funny way. If you really want to say, is it a priority scheme? It kind of is. It's first come, first serve. In the same, because it's not preemption. So there's really not any issue in terms of picking priority. So they're in a way the equal priority. You come in that order. That's you. So a priority base probably makes a little more sense. I mean, it's certainly applicable to preemptive ones, but it also applies to when you are in the wait queue, right? What do you do? Can you reorder while in the ready queue or wait queue? Okay. Now, in real-time systems, certainly priority-based scheduling is used a lot, and deadline can be used to be priority as well. And now, age of process could also be priority. So that's one very common way to prevent starvation, because as a process ages, in other words, stays in the ready queue for long and never gets to execute, well, that's how you define the age. Then you give it higher priority. Eventually, it gets to run, right, before too long. And there's hybrid schemes and mixing different kinds of priorities. So that's one way. So starvation is definitely one problem with scheduling. You can imagine in this case of shortest job first, do you think you can have starvation? Yes, because you happen to load up a big shopping cart, and it happens that everybody else just wants a candy. So they all cut in front of you. They all cut in front of you. Right? So you just wait there forever, and then you saw, I mean, even in that case, you waited a long time, right? And so that means some guy with a big shopping cart could be sitting there from morning till evening and still be waiting there just because it's nice enough to let everybody buying candy go in front of them, right? So that is starvation problem, right? So they got their lunch, they want to prepare lunch, but then it probably spoiled by the time they check out. So that means indefinite blocking. And that's process ready, but doesn't get picked to run for a long time. And so this actually happens for real. And so at MIT, they had an IBM machine, which was started in the 60s. And then by the time they wanted to take it down, shut it down in 1973, they found, oh, there was a process from 1967 that never got to run. So that's a real long starvation, okay? So, and solution is by aging. So you want to adjust, go back and readjust the priority of the processes based on how long it's been in ready queue, and then promote them so that way you can do it. So one way is to increase the priority level by 1 every 15 minutes. I mean, but you could do even shorter than that. Now, multi-level queue scheduling is a way to separate out your ready queue into separate queues, different queues. So, for example, we could have one for foreground, one for background. Foreground could be doing interactive. Background could do batch, like loading, uploading, downloading, saving to disk, and all that. So these processes stay in the given queue instead of moving between queues. And each queue would have its own scheduling algorithm, most likely priority based. It could be round robin for one, first come, first serve. So this is an example where you're trying to match the characteristics of these processes with the appropriate scheduling algorithm so that overall everybody wins, right? And so one example given in the book is your ready queue could be separated into like one for real time, one for system tasks, one for interactive jobs, one for batch, right? And real time will always get highest priority, so you schedule the real time ones. If you don't have real time ones to do, then you go down to the next one, the system ones, and then system would do. And of course, you can cap the utilization of each queue, so that way you don't starve any of the lower priority queue, right? And then within the queue, you can then prioritize all you want. And now, but you do need some way of defining the scheduling policy between queues. In other words, when do you get to run each queue? So you could do the fixed priority way in that the real-time one always gets the highest priority, and always fixed. Is that going to work? Well, yeah, that might serve the purpose of real time, but then what about the other ones? Could they possibly starve? Well, yeah, they could. Or another way would be to apply kind of round robin, but uneven round robin. So maybe system ones get more slices, more time quantum, and then the leftover, well, the other ones, they still get round robin, but they get proportionally fewer, or I don't know. Or maybe they come in, certain ones come in more often, other ones get just more total time slices. Okay, so there are different variations possible. Now, here is another scheme called multi-level feedback queue scheduling. Okay, what's the difference? Previous one, multi-level queue scheduling. Here, multi-level feedback queue scheduling. Difference is that feedback. But what does that mean? This means, well, previous one without the feedback is just fixed priority. With each queue has its fixed priority. Or I should say, no. The processes stay in their own queue. That's without the feedback. It's here. It could be fixed priority or dynamic priority between queues. But each process, once it's created, stays in that queue. That's multi-level queue scheduling. Now, multi-level feedback queue scheduling allows you to move a process between different queues. Okay, you get it? So the feedback part indicates ability to move a process between different queues, as opposed to once it's created, it stays in that queue. And so aging can be implemented this way. And so that this way you separate processes based on characteristics of CPU burst, which is more of a dynamic kind of characteristics. In other words, it could be longer or shorter over time, depending on what you're doing. And IO-bound interactive process may get shorter CPU bursts, and CPU-bound ones get longer CPU bursts in lower priority queue, for example. Right? And so there are different ways. Of course, you have to pick your time quantum. And so you may pick different time quanta depending on if you want them to be more CPU-bound, IO-bound, or so forth, right? So you could have one where Q0 would be first come, first serve with a time quantum 8 milliseconds. But you say, what? First come, first serve? Isn't that supposed to be non-preemptive? Well, yeah. So this is more like round robin, right? And whereas Q1 could be first come, first serve. Well, here, really, it means round robin because if you do preemptive with a quantum, right? Then also this allows you to do this. So if you don't finish before your quantum, you actually get moved to a different queue that has a longer time quantum, but it has a lower priority, right? So the feedback is what allows you, what drives you to move a process between different queues. And each queue may have longer, shorter quantum and so forth, and associated with a priority. So that way, you get to execute longer, but it's lower priority, right? And so because your characteristics is you need more CPU time, so I don't want to interrupt you as often. So overall, everybody wins. Multi-level feedback queue is defined by number of queues, scheduling policy for each queue, condition for upgrading or downgrading a process to a higher or lower priority queue, and the associated policy as well as the associated time quantum, and condition for choosing which queue for the process to enter. Maybe you don't just go up one or down one, maybe you can jump directly to a separate one, right? So that's another choice. Now, so we're gonna, do you have a question? Okay, so to do thread scheduling, now you need to consider some factors. It's called a scope of contention, because you are competing over resources against somebody else who's sharing the same resources in the same process or the same processor. So if you're doing only user level threads, that means it's running within the process. The kernel probably doesn't even know that you're running multiple threads, right? You're just creating that pure software abstraction, which means, I mean, the process is given this much resource to work with in terms of cache well, I mean, cache is CPU, but in terms of memory, in terms of your number of files you can do, all that, and they have to compete, right? And so, and this is the case for both many to one. In other words, many threads, user threads to one kernel thread, as well as many to many, because the number of kernel threads that can run is fixed, and so they have to compete, and you need to be aware of the resource users as well as some architecture effects, including the memory effect, cache effects. Otherwise, the performance can suffer. System contention scope would be that you schedule these kernel threads onto available CPU, but then what you're competing with when doing thread scheduling this way is competing among these the kernel threads in the system, right? Because you're using system level resource, not just process level. And for pthread scheduling, you could actually pass an additional flag to see if you want your thread to compete within the process or at the system level, right? And so it's implementation dependent, but really POSIX threads really just say, okay, this is a spec, and how you implement it, or you implement it in a way consistent to this, but you don't have to support it. So if it's within the process, then kernel really doesn't have to do much with it, right? But then if it's system one, then yes, you actually are competing at the system level, and it would be actually nice for the kernel to know this option. Now, Linux, on the other hand, and even Mac OS to a large extent, only supports the system level contention scope. Okay, so I'm going to spend a little time talking about the multiprocessor scheduling issues, as well as some of the architecture issues before going into real-time scheduling. So for multiprocessor scheduling, you actually have to know many varieties. One is, I mean, this here is just on scheduling, okay? So this is characterizing scheduling. So on a multiprocessor, what can you do? You can do scheduling on one processor, and then that processor does a schedule and then tells everybody else, okay, here, to run this, here, run that, right? So kind of a master versus a bunch of slaves type of thing. Or you could have each processor run its own scheduler and dispatch its own, right? So if it's kind of this single master, bunch of slaves, that scheme is called asymmetric multiprocessing. If every processor gets to make its own scheduling decision, it's called symmetric multiprocessing. Kind of a counterintuitive. I mean, you say, really? Asymmetric, you might think the multiprocessing is like some would do run a different program than the other. No, that's not what it's talking about. This is just talking about multiprocessor scheduling, okay? So in the asymmetric case, you have one central processor that's called a master server, and it's scheduling these processes on behalf of all the other ones running in the same multiprocessor system, okay? And all the other ones just say, okay, whatever process you tell me to run, I run, okay? So they just have the dispatcher, but not the scheduler. And the scheduling is much simpler because it's one master server just runs its own code. Now, it doesn't have to share this with anybody else. It just tells somebody else to do it. But it itself could become a bottleneck. Symmetric actually has two options. Well, you say each processor schedules itself, but does each one have its own private queue, or can you allow these processors to share the same ready queue, and then pull from that ready queue, and then it decides well, what to schedule? So that would be option 2. So you might think option 1, but option 2 actually is used a lot because you do want to keep these processors more or less utilized. And so option 2, sharing the ready queue is actually the most common option. Okay, and it does need synchronization mechanism as with any shared memory type of multiprocessor. So now we're gonna digress a little bit into the these what's called SMT. We mentioned a few times, but this chapter, the book actually has more coverage, and they actually updated some of the coverage. So I'm gonna spend a little time talking about this. So trends in multi-core processor. One is multiple cores on the same chip. Why? Because people really ran out of tricks building, trying to crank up the clock speed. Pretty much tops out at 3 gigahertz. You don't really see 4 gigahertz processor or 5, 6, 100 gigahertz, right? No, it's for the last couple, last decade or two, it's been kind of capped at 2 or 3, about 3 gigahertz and so forth. And why? Because clocking faster means the chip gets really, really hot. They don't even know how to cool it. And some might project, so if you run it like 4 or 5 gigahertz, it's hotter in terms of thermal density than sun. So that's bad news, right? And besides, mobile processors become much more important. And so, and power doesn't scale linearly. Power scales quadratically. So that means if you want to run fast, you have to crank up your voltage, and you have to consume and then actually power increases by n of voltage squared. But then what does that mean? That means power reduces quadratically as well. So if you lower clock rate, lower voltage, your gain is a lot more than linear gain. Okay, so that means it actually is more energy efficient if you run more cores and hopefully running them in parallel than running a single process at a very fast speed, at higher power. Right, the power is much more advantageous. And besides, the silicon technology got much cheaper. They don't know what else to put on there. Okay, just put more cores on there, just duplicating, right? Not a lot more design. You have to do the interconnect, but then that also makes sense. And so that's using more parallelism to make up for potentially lower per core performance due to lower power, lower voltage, lower clock. Okay. And that makes sense for mobile. Now, each core is improving in the sense of multi-threads per core. So it looks like a uniprocessor, but actually the hardware supports multiple program counters, multiple register sets, multiple PSWs and all those. It's like, well, how does that work? Well, actually it's nothing new. In fact, this was invented by IBM in the 60s. Over time, like CDC, which you probably don't know, a company that already went out of business, but Terra, another supercomputer company in this day, they had like 128 thread single processor. It's like, what? Well, that's because they really wanted to do something about this memory latency. Okay, used to be that you pay 10 cycles latency to fetch from memory. Then this gap becomes bigger and bigger, and then it's 60 cycles, and it's 100 cycles, there's 1,000 cycles. The memory hasn't kept up with the speed. And you put a cache in there, but then what if you have a cache miss? You still pay that cost, right? So that's why they say, okay, let's try to all the ways possible to keep the processor busy because you're reusing those same functional blocks. Maybe you're just switching between these register sets, program counters, so it makes sense, right? So that's not a new idea, but of course Intel tried to make it. Oh, look, we came up with this new idea called hyperthreading, a new buzzword. Well, it's not really a new idea. But they just did it pretty much for like 2 hardware threads per core, because that's straightforward and simple to do. Okay, but so it's really, you can think of it as single processor, but they keep multiple register sets. A lot like how like 8051 keeps these register banks. You're just switching between banks, except their banks include program counter. You have a program counter 1, program counter 2, program counter 0, one for different hardware thread. Okay, so that way it makes your threads package so much easier to write. You don't have to do our save state, restore state like that. Just do a bank switch. Very easy. In fact, the processor could even do that automatically for you. Okay, so that's called SMT, Simultaneous Multi-Threading, also known as hardware threads, also known as chip multi-threading. Okay, depending on who you're talking to. So CPU maintains multiple program counters, register set, so that they look like logical processors. But can you run both threads at the same time? No. You're running only one thread at a time. It just hardware supports these register sets, including program counter, so that you don't have to create these concepts just in software. But really, they are. It's really just running one thread at a time. And really, it's during the time when the processor has to stall, whether due to memory, due to whatever, trying to keep the processor utilized by switching to a different hardware thread, hoping that it doesn't have to pay that penalty, hoping that it gets the cache hit, hoping you can do more useful things, okay? Now, this is done not all SMT are the same. One is called coarse-grained, the other is fine-grained. Now, coarse-grained would switch, like I was saying, when you have a memory stall, right? So it has to do a load and store. Oops, sorry, it's not in the cache. Have to go to memory and have to wait 1,000 cycles, really? Okay, then the processor says, okay, well, let's switch the thread. And hopefully you get a cache miss. Of course, if you get a cache miss again, then you have to stall anyway. But then you at least tried. But if it's a cache hit, great, you can make progress. Now, fine-grained, on the other hand, actually is interleaving threads at instruction boundary. Okay, and so this way, this is much trickier to design a processor this way. Now, on the other hand, coarse-grained is a little easier in the sense that you know when the pipeline bubble is going to occur, right? Because load is going to stall anyway, so that just means it has to flush the pipeline. And then during that time, that's when it starts a separate separate thread, and that has to take some time to fill up the pipeline. Fine-grained actually does the very fine-grainedly because you could have pipeline bubbles even without doing even without a memory stall, right? You've all taken computer architecture, yes, right? Like when you do a branch, you may have a stall. So some architecture have like a delay branch to fill that, but there could be other cases where you have hazards. Remember? Yes, please say yes. If not, go back to your architecture class and review this. So there could be other reasons than memory stall that could cause pipeline bubbles. And these guys, they're trying to do, okay, well, it's a pipeline bubble. Let me fill in a little instruction during that pipeline bubble. So at least I keep the processor utilized, okay? So that's fine-grained. Of course, that's a lot trickier because you got to think about, oh, when pipeline bubble is detected, that triggers switch to a different instruction from a different thread. Has a lot more to maintain, okay, compared to the coarse-grained one. And multi-threaded scheduling on multi-core, well, the thread scheduler needs to consider cache behavior as well, and resource sharing. Otherwise, having multiple threads could actually run slower because each thread could increase the demand on the cache, right? If they're not running the same code or not accessing similar data, that means it's going to try to displace, or it's likely to displace some cache space just for its own working set, right? Remember working set from your architecture, right? Say yes, please. So that puts pressure on the cache. If the cache is not big enough, they start interfering with each other. So then more cache misses is just bad news, right? So just having more hardware threads doesn't mean you actually run faster. You're likely to, in practice, you're going to run faster, but no guarantee. So processor allocation could be an important issue because you do want things that don't interfere with each other as much. So you select which software thread to run on which hardware thread, or these you might call virtual processor, right? And also the intra-core scheduling or intra-core threading. So each core decides which hardware thread to run.
然后这个问题还要分
well, it's very specific to how each architecture works. This is really for your own interest. This is not a fundamental architecture concept, so I consider this mostly outside the scope of this course. But I'm just mentioning it so that you, hopefully it's a way for you to connect to, say, architecture course and more advanced the OS courses. This is more of an intro course, but okay, so now load balancing is another important consideration for these processors, multi-core processor or multiprocessor, because you have these processors available, and the whole point is you want to keep them utilized. Otherwise, why pay extra price for those processors, right? And so if you're using the symmetric case, that means each has its own queue, then they would each try to keep the CPU loaded, but then that means they could run out of some process to schedule. If you have shared queue, you don't really need separate load balancing. Why? Because when a CPU runs out of work to do, is idle, well, you just go pull the next one from the shared queue, right? So that way it's automatically load balanced. But load balancing, even the term actually can take on different meanings. Because what does it really mean to be load balanced? So in the case of private queues, you may have the same number of threads. Does that make it load balanced? Maybe, maybe not, because threads aren't all equal. Some may be more I/O bound, some may be more CPU bound, right? So if you just base your load balancing on the number of threads, who knows? Is it really load balanced? I mean, on the surface, it kind of looks like that, but in practice, it might not be. And what about equal distribution of thread priorities across all the different queues? Maybe, maybe not. So, right? So you want not just they have the same number of queues or comparable, but you have the same mix, right? Different priorities. Anyway, so load balancing would mean, in the case of symmetric, that is, each process schedules itself. And you can do so with either push or pull. Push means a processor says, "Hey, I'm overloaded. I got too many tasks. Let me push them out to somebody else." But then that requires it to know who else has the capacity to take more processes. Pull means, "Hey, I'm idle. Give me some work to do." Okay, so it grabs from somebody. But then, how does it know who's overloaded? Okay, so they still need some mechanism for communication. So there's at least these two styles.